this continuous stream of glowing data packets flowing through a single, narrow conduit. This represents the baseline architecture of the modern web. Front-end clients constantly request and receive these payloads of raw, unformatted data arrays from backend APIs. When this payload arrives at the client, it is largely unusable in its native state. The data often contains excess properties, requires mathematical aggregation, or needs filtering before it can be rendered into a user interface. It requires transformation. But retrieving that raw data introduces a critical physical constraint: network latency. Fetching data from a distant server takes time, sometimes milliseconds, sometimes seconds. This latency collides directly with JavaScript's rigid architectural constraint. JavaScript operates on a strict, single-threaded execution loop. It can only process one command at a time. If it waits idly for a network request to finish, the entire application freezes. Mastering modern JavaScript requires solving these two problems simultaneously. Engineers must shift to declarative data transformation to process arrays cleanly, and evolve their asynchronous control flow to prevent systemic blocking. Building robust applications means decoupling the exact timing of data retrieval from the logic used to manipulate that data. Consider a standard data payload, an array containing multiple item objects, where each object holds a specific name and a price. The traditional imperative approach to extracting the prices from this array involves constructing a for loop, establishing a volatile index variable, and manually pushing each price into a separate external array line by line. Modern functional paradigms replace this manual tracking with built-in declarative methods that handle the iteration automatically behind the scenes. Watch this array of complex objects pass through a horizontal processing line. By applying the map method, we extract a specific value, like the item's price. The method iterates over the payload and returns a brand new, identical length array of just those numbers, leaving the original dataset completely untouched. The filter method applies a different logic gate. It evaluates each item against a specific condition, such as whether a price is greater than 100. It then returns a new truncated array containing only the values that passed the test. This behavior differs precisely from the find method. Instead of processing the entire array to return a new list, find halts execution the moment it identifies the first matching object, returning that single object alone. If you only need a Boolean evaluation, JavaScript provides sum, which returns true if even a single item meets the condition, and every, which returns true only if the entire array passes. These declarative array methods eliminate the need for external state mutation. They create highly predictable, immutable data pipelines, where inputs reliably produce exact outputs. Often, transformation isn't enough. You need to aggregate that transformed array into a single metric, like calculating the total cost of a shopping cart. This requires folding the data down using the reduce method. Notice the central block in this diagram. This is the accumulator variable native to the reduce method. It initializes at 0, absorbs the first array value, updates its internal numeric total, and waits. As the method iterates, the accumulator dynamically tracks the running total, sequentially absorbing each subsequent item until it yields a single final integer. The imperative alternative requires declaring a global variable completely outside the loop and constantly overriding it, opening the door for other functions to accidentally interfere with that variable. By utilizing reduce, the state tracking is completely encapsulated within its own execution context. It isolates the logic and prevents external variable collisions. Once you have the logic to manipulate data, you must confront the latency of acquiring it. Consider a dependent sequence. The application needs to fetch a user profile, extract the unique user ID from that profile, and then use that ID to fetch the user's recent posts. Recall the rigid constraint of the JavaScript call stack. It processes operations on a single thread. Look at this execution timeline. If JavaScript attempts to run these two network requests synchronously, line by line, it triggers a crash. The engine will execute the request for the user profile, and while waiting for the server to reply, it immediately moves to the next line and attempts to fetch the posts. Without the user ID, the request fails. This creates a paradox. The network tasks must fire in strict chronological order to succeed, but they cannot block the main execution thread while waiting for the server data to arrive. Handling high-latency input and output requires an architectural structure capable of deferring execution without freezing the global environment. The foundational solution to this asynchronous routing was the callback function. A callback operates by passing an entire function, like the command to get posts, as a literal argument inside the function requesting the user profile. This cleanly defers the execution. The engine knows not to invoke the post retrieval until the user profile operation reports a successful completion. But as applications scale, a severe architectural flaw emerges: callback hell. Notice the shape of this code block. When you have 3, 4, or 5 dependent network requests, each function must be nested inside the previous one, forcing the structure to indent deeply inward to the right. Engineers call this the pyramid of doom. It destroys code readability, making it incredibly difficult to track the actual sequence of events. Furthermore, error handling within this structure breaks down. If a nested request fails deep inside the pyramid, that error cannot easily bubble up to the surface for the application to catch. Callbacks successfully bypassed the single-thread latency constraint, but as the dependency chain grows, the resulting code becomes difficult to refactor and debug. To fix this, modern JavaScript introduced promises. A promise is not a function. It is a proxy object that represents the future resolution, or failure, of an asynchronous request. Instead of nesting functions inside each other, promises utilize a .then chain. Once the user profile resolves, the .then method passes the user ID directly down into the subsequent request for the posts. This flattens the execution logic, pulling it out of the deep nest and stacking it into a clean vertical sequence. To further simplify the sequence, JavaScript introduced the async and await keywords. Async await is syntactic sugar built directly on top of the promise architecture, designed to make asynchronous code read exactly like synchronous code. Look at this execution thread. When the engine encounters the await keyword prepended to a fetch request, the local thread branches horizontally to process the waiting period, while the main vertical thread continues flowing downward unimpeded. The keyword pauses only the local function's execution context. The global JavaScript thread remains completely free to run other tasks and render the user interface. Visually, async await code sits perfectly flush against the left margin. It reads chronologically, top to bottom, removing the .then chains entirely. It restores linear readability to complex logic, while preserving the necessary non-blocking asynchronous behavior under the hood. You can see the evolutionary geometry of JavaScript control flow in this comparison. We moved from the nested wedge of callbacks to the chained blocks of promises to the perfectly vertical structure of async await. Through each iteration, the syntax is changed, but the operational goal remained constant, managing chronological order in a single-threaded environment. Modern data pipelines merge these two domains. They rely on async await to secure raw data arrays safely across the network, and declarative methods like map, filter, and reduce to transform those arrays upon arrival. Combining these abstractions produces codebases that are highly readable and resistant to errors, from the initial backend fetch to the final front-end render. By abstracting the manipulation of state and the management of asynchronous time, modern JavaScript provides a framework for building complex, non-blocking applications while keeping the underlying logic